Today we are going to perform a shape optimization on a steering knuckle that you might find in a ground vehicle in the automotive industry. Now we are going to be using Nastran Sol 200 to perform this optimization, and this is what you can expect. We are going to take a few regions of this model and we're going to specify some shapes. These shapes are going to either expand or contract. The goal is to minimize the mass from about 8.08 and reduce it to about 0.02. At the same time, we want to make sure that the max von Mises stress is less than an upper bound of 40. So here's just another image of what the plot of the von Mises stresses look like in the model. So this is going to be our goal for this exercise. And now just to quickly summarize how this model is constrained, this model is fixed in the indicated hole. At the same time, we're going to apply some forces and some torques throughout this model, and in total we're going to have about 12 load cases. Now, there are two regions of this model where we have elevated stresses, and this is where we're going to create our shapes to hopefully make sure that we can minimize the mass while making sure that we're less than the upper bound of the stress that we specify. And on this slide, we have the optimization problem statement. It's always important to sit down, draft what your variables are, what your objective and your constraints are. Here, we're going to say that the objective is to minimize the mass or the weight while making sure that the von Mises stress at the center of the elements is less than 40. And here in these different colored regions, we're going to specify element faces that are allowed to either expand or contract during the optimization. So this is a more realistic model that you might have in your scenario, and I wanted to show you what the process will be like if you want to perform shape optimization. Now, before I continue on, if you are interested in optimizing your Nastran model, if you want to use a gradient-based optimizer, if you want to use machine learning, if you want to learn how to perform optimization, you're always welcome to contact me at the email address that you see here on the screen. Now, before I go ahead and start this exercise, a quick reminder. The Sol 200 web app is a collection of web applications. Each one is designed to help you optimize your Nastran model. If you can optimize your Nastran model, you can optimize your real world structure or your real world mechanical system. If you are dealing with composites, you can use some of the composite laminate tools to optimize apply shapes or the stacking sequence or the ply number. If you want to use machine learning, there's a web app for that. If you want to use size optimization, there's also a web app for that. And today we're going to be using the shape optimization web app to perform the shape optimization today. So now let's go ahead and exit here and start the exercise. Now, one quick assumption I'm making in this tutorial. I am assuming that you have already gone through the introductory shape optimization exercise that's called shape optimization of a cantilever beam. This goes into great detail, the fundamentals of shape optimization. I am assuming that you have thoroughly gone over this exercise. In this tutorial, the steering knuckle, I'm assuming that you're already experienced with shape optimization. So a lot of the fine details I'm going to skip. Now here, you'll find this tutorial of the steering knuckle. For this link, starting BDF files link, click on that link, and then in your downloads directory, extract the contents of that directory. This is going to have two bulk data files. The first bulk data file is the steering knuckle. All the elements, all the nodes or the grids, all the materials and the loads, even the 12 load cases have already been defined. In the second bulk data file, we have defined the weight, we have defined constraints on some of the stress outputs of the elements, and here you see the upper bound is 40. The only thing we have to do now is specify shape variables, and then we can perform this optimization. So now let's go ahead and go back to the home page of the web app and open the full list of web applications and scroll until you find the viewer. This is where you get to upload the bulk data files for the steering knuckle. And remember, I'm assuming that you've already gone through that first tutorial. You already know how to rotate the model, move it left and right. You already know how to open the shapes panel. You know how to change the color. You know how to create your shapes here. You know how to enter the pick mode and drag the pick sphere. I'm assuming you already know how to do this from that other exercise, the very simple and introductory exercise into the cantilever beam. So here, let's go ahead and create 4 shapes. Let's go ahead and rotate the model a little, and let's go ahead and zoom in into the first region. So let's go ahead and maybe reduce the width or the size of that panel. And here is the first phase that I want to either expand or contract. Let me zoom out a little. If you look in the PDF document, you'll see that this region and this region of the initial design have a high stress concentration, if you will. What we want to do is go ahead and maybe modify some of the geometry here, some of the boundaries, so we reduce, or rather we make sure that the stress is within our allowed limit. So here, let me exit here and go back to the web app. So this is the first region where we have a stress concentration. So we want to let the boundaries move. And what I'm going to do is I'm going to select some of the primary faces first. So that would be these faces that I'm highlighting. These are going to either expand or contract during the optimization. And then let's go ahead and repeat the process for the second shape. So what I'm going to do here, so I'm going to select these element faces. So this is the second region that is going to be allowed to either expand or contract. Now here, let me make sure I am selecting the right elements. Let's go ahead and select these faces. And now let's go ahead and run MSC Nastran right now. Right now, Nastran is going to compute the shapes for the indicated regions. Now, so far, I've only selected expand or contract regions. That's what I've created so far. Now let's go ahead and preview a shape change. And this is what that preview looks like. If we zoom in a little, we get this black line. And this black line represents the boundary of the initial model. And here in this new boundary is what the shape is after the shape is changed by an increment of 1. So if you were to measure the distance from this original boundary to the new boundary, the distance is approximately 1. So that's what you're measuring here in this test value. Now, let's go ahead and do this a little bit more. Let's increase the change by an increment of 5. What would that look like? Now, you already see what the problem is when I expand or contract only on this set of element faces. We have the issue where the adjacent elements are not expanding or contracting with these primary faces. So we should introduce stretching in those adjacent element faces. So if we go back here and we zoom out, click on this plus icon here. This new picking sphere will allow you to pick element faces that are going to either expand or contract during the shape optimization. And you'll notice that in the secondary faces, the color of the faces are a lighter color. So let me just go here and just continue selecting these element faces. And this is where you kind of use your intuition. You tell this, or you prescribe, or you define which regions are going to be expanding or contracting. And here I'm just looking at my notes to make sure I'm selecting the right element faces. And here I can see that I go up to 2. And then here we also want to let these other faces stretch with the primary face. So let's go ahead and do that right now. And I think here I select 2. Right, okay, let's go ahead and just continue selecting these faces. Okay, I think this is looking good. And let's rotate the model and also do the same for this region. Now, this is going to be a combination of trial and error and intuition. So let's go ahead and now rerun Nastran. And let's look at what this new shape looks like after we introduce elements that can stretch. So you can see that the shape looks better than before. These element faces here are allowed to stretch when this other primary face is allowed to expand or contract. And now, this is where we find sort of the limitation in this way of performing shape optimization. Maybe we want to contract. We want to push this element face in this direction. But here, since in a way we're kind of pushing it with an actual load, internally we're pushing it with the internal load, we're going to have this corner of these elements kind of, what's the word I'm looking for? Go outside the original boundary. And this is okay. This tool is not going to be a tool that's going to be very precise. This tool is mainly used to suggest, propose some possible shape changes. You're not going to get exact precision from this tool. But this is okay. Since we can use this to approximate the changes, this is going to be useful in the end. So now, let's go ahead and look at the shape change for the second shape. So that would be the green shape. What happens here? Let's see if we're comfortable with the shape change. And again, we have not included stretching. So if we go too far with the contraction, look what happens. We'll start to get a mesh distortion if we do not have stretching in the adjacent elements. So now what are we going to do? We're going to repeat the process like we did before. We're going to click the plus icon for the second shape, and we're going to select these elements. So let's go ahead and move the mouse cursor and select the elements that you see me select here on the screen. And let me make sure I'm selecting the elements. Now, you don't have to be exactly matching the exercise, the PDF. This is all approximate. So let's go ahead and do this. Let's go ahead and rotate the model again. It's going to repeat the process for the other side. So here for the other side, I'm going to select these element faces that are going to be allowed to expand and contract. And then here we'll do the same for these element faces. Basically, generally, for any adjacent faces that are going to expand or contract, you also want to set the adjacent faces as secondary faces that are going to expand or contract. So again, this is going to be trial and error. This is going to be some intuition. And this is looking better. I want to prevent these adjacent elements from being distorted. Now, you notice one thing in this current shape change that I'm previewing. Maybe you don't want to allow this much shape change during the optimization. So let's go ahead and look at what these other values look like. Suppose I'm going to experiment with increments of -6 for the shape change. So maybe I look at this and I say, okay, maybe this is the most amount of shape change or contraction I want to allow. So then what we can do, we can go up here to the upper and lower bound, and I can specify that the lower bound is going to be -6 for these two shapes. Now, what about expansion? What does that look like? Let's go ahead and look at what an expansion looks like if we increase the shape by an increment of 10. So again, if you were to measure the distance from the original boundary line to this new boundary line, you're approximately going to get an increment of 10. Now, what does that look like? Does the mesh look distorted or does it look relatively smooth? We want something smooth, and here maybe this is a little too much. Let's look inside. And now we see one issue here. This face is now intersecting this other face. This is indicating that the shape change is too much. Let's bring it down a little more. Maybe let's try 5. Let's make sure that these two faces are not intersecting each other. And let's look inside again. And let's go ahead and just go back here. Click display preview shape and let's look inside. And now this looks a little better. Before, this phase was coming into contact with this other phase. Maybe we didn't want that. Some might argue that, okay, maybe there's a shape change here. We don't necessarily want such an acute angle here between these two element faces. It's up to your discretion how much shape change you want. But here I'm going to leave it at 5 and 5. Okay, now let's go ahead and create some additional shapes. So let's go ahead and zoom out. And let's focus on this region of the model. What are we going to do here? Let's create 2 more shapes. And what I want to do now is for one of these shapes, I want to introduce some expansion or contraction for these elements. Let's go ahead and select these elements. Do you see me highlight on the screen? Now, the size of the picking sphere is very small. Sometimes it helps to increase the size. Here in this box, you can increase the value to maybe 10. And this is in units of millimeters or inches, depending on what your model is defined in. But here, I think I'm really used to 1, so let's go ahead and use 1 for now. Let's go ahead and select all these elements. Now let's rotate the model a little. And let's continue selecting elements. And right now I'm selecting the element faces that are going to either expand or contract. And remember, you have to introduce stretching in the adjacent elements. If you don't do that, you might get some mesh distortions. So let me go ahead and create another shape. So this next shape is going to control expansion or contraction of this cylindrical part of the model, if you will. So let's go ahead and rotate the model again. Let's go ahead and select the element faces on the other side. And let's go ahead and make sure that we've selected all the faces on the cylinder. And now let's run MSC Nastran. Let's create some new shapes and explore what the shapes will look like for this. Now, for the preview, I'm going to experiment with values of -6. So see what happens when we change the boundary by -6. Now, this doesn't look good if you want to, what's the word I'm looking for? Have some smoothness in the shape. So what do? Here, let's focus on the cylinder for now. Let me click on this plus icon. Let me select these top faces as stretching faces. So let me go ahead and move this around the top. And let me do the same for the bottom. Let me select these faces here. And these faces again are going to be either stretching or contracting for the most part. So let's go ahead and do this. Let's run Nastran again. And let's look at what the new shape looks like. It should be more cylindrical after this. So this looks slightly better. Let me turn off some of the other shapes actually. And this is what the cylinder will look like if we increment it by -6, or we contract the shape by -6. This might be too much shape change. So let's go ahead and contract it by -3. And here, this is something we can work with a little better. One thing to point out here is that the cylinder is not perfectly smooth. You can see there's sort of a kink here. And again, that is with this shape optimization procedure we're using, some could say this is a limitation. And I'll say it again. This tool is not meant to produce a precise result. This tool is meant to give you an approximation of what some of the dimensions should be close to. So here, I've deemed -3 as a good lower bound. So let's use -3 for the lower bound of this shape. Now, let's create some stretching in this third shape here. How do we do that? We're going to go ahead and click this plus icon. And remember, for the adjacent elements, it's always a good idea to introduce some degree of stretching. So that's what I'm doing. These secondary faces are going to have some degree of stretching during the shape optimization. Now, for these element faces that you see here that are gray, let's go ahead and ignore those faces for now. Let's run Nastran again. Nastran's going to compute some new shapes, if you will. Let's go here and turn on just the preview for the third shape. And look what happens when we contract that face by -6. It's too much shape change. So maybe, let's go ahead and maybe look at a shape change of -4. What does that look like? Is this any better or worse? And actually, let's go back to -6. Maybe there was the order of the shape change was out of order, so that's why we have a really unusual shape. But here, when I look at -6, this looks like something I can work with. Here, if I look at the element faces on the side, you can see that for the most part, they're relatively flat. But you see some slight perturbation, some slight deviation from the original boundary. And again, I'll say it again. This tool is not meant to give you a precise result. To get a precise result would take you days of experimentation with the bulk data entries in the auxiliary model. This approach that's used by the web app is a good balance between an approximate design and speed. You see how I'm able to quickly select these faces and get an idea of what the expansion or the contraction will be for the shapes. I don't have to spend weeks or hours to do this. So now let's go ahead and look here and see where we're at. And let me turn on all of these. Let me go ahead and test it. If the optimizer hits variable values of -6 and -3, what does my final shape look like? I want to make sure that there's no mesh distortion for the lower bounds of these shapes rather. So for -6 and -3, the shape does not look distorted, which is good. Let me rotate the model a little. Okay, things are looking good. Let me update the bounds actually. So -6 and then -3.0. Now, so far we've been working with contraction or negative shape changes. What does expansion look like? Let's go ahead and expand all these shapes by an increment of 10. Or +10 for expansion. What does that look like? Do things look good or not look good? Let's go ahead and maybe focus on this other region of the model. Now, here, the first thing you'll notice is in the cylinder. The cylinder is too wide, and it should not be wider than the other regions. So what do we do here? What we can do is reduce the shape change value to 2. So at most, we're going to have an expansion of by an increment of 2. So that's what that will look like. What about this shape, Y3? Let's reduce it to maybe 3. So at most, we're going to have an expansion of +3. So this is something better we can work with. So now let's go back here and let's update the upper bounds to limit the amount of expansion. And let's look at the other region. Here, when we look at this region, maybe we say, you know what, that's just too much expansion. Maybe we don't want that much expansion for this region of the shapes. So what do? Let's go ahead and test some shape values, maybe 5. And here we say, okay, you know what, maybe this is a little better. It may not be perfect, but that's okay. We're using this tool to approximate some values for new boundaries, if you will. So here we're going to say that the maximum amount of expansion for shapes 1 and 2 are going to be +5. And then for Y4 and Y3 and Y4 rather, it's a max of 3 and 2. Now let me go ahead and see my notes and see if there's anything else we need here. Nope, things are looking good. Let's go ahead and click on download and download these new bulk data files. Let's go ahead and extract the bulk data files. And we'll go ahead and start this optimization. Now, while the optimization is starting, let me go over a few comments. Number 1, if you go to the new entry section, you get a small summary of the changes that have been made to your bulk data files. So here you can see that at the end data delimiter, a new bulk data section for the auxiliary model has been added. Here are some other changes that have been made. I think another thing to do is to actually open the design shapes for psolid1 bulk data file. Here are all the desvar, the DV shapes, the B&D grid entries to define those shapes that we created in the web app. I'll say one comment about the DVB shape entry. By default, the scaling factor is 1.0. If you are using a scaling factor of 1.0, you're most likely setting up the problem incorrectly. You need to use carefully selected scaling factors. And again, I will refer you to the introductory workshop for shape optimization. So here we go back to the user's guide and go to shape optimization and click on the first PDF. There's an appendix. In the appendix, it goes into detail how to carefully select these scaling factors. So I refer you to this first introductory example for that. Now let's go back here and look at the optimization results. Let's go ahead and go through a procedure of analyzing the results. First question to ask, did we minimize the mass? Here it looks like we did. Now, number 2, do we have a feasible design at the end? A feasible design is when the max normalized constraint value is either negative or very close to 0. Here, we see that the final value is actually negative, indicating a feasible design. What about the design variables? When you look at the design variables for the shapes, the values here are not, how do I say, the shape increments that we spoke about before. This 10 does not mean that we incremented the shape by 10. This is how you review the shapes. After the first design cycle, the variable value is 9.46. So then we'll do this, 10 minus 9.46. This gives me 0.54. So that shape has changed by a value of 0.54. So that's the distance between the original boundary. Let me see if I can find a boundary here. So here's a boundary. So here in this black line is the initial boundary of the shape. Here in this other preview line is the new boundary of the shape. This 0.54 is going to correspond to the difference approximately between the original boundary and the new boundary. So you'll see a few things. Here it's contracting because the plot, if you will, is decreasing. Let's see if there's a shape that actually increases. It looks like all the shapes are decreasing. So instead of looking here, what we can do is actually open a preprocessor and look at the results of the shapes. So let's go ahead and do that right now. And I'm going to go very quickly over how to do this in Natran, but if you look at the appendix for this workshop, it'll give you more details on how to do the steps that I'm going to go over really quickly right now. So let's go ahead and import the Nastran model. So let's go ahead and import model.bdf. And let's go ahead and import the H5 file. Click apply. And now let's go over the results. So when you look at the results, you're going to have a lot of rows. And let me quickly go over what all these rows are. The last letter M rows are going to correspond to the 4 shapes that were created in the web app. So here, let's look at the first shape. Click apply here, maybe reduce this a little, click apply. And maybe this view doesn't look so clear, so let's do this. Let's go to this third button or icon. Let's change this to shaded, change the color. Let's change this to free edge and click apply. So I believe this first shape is going to be here. So this is what the first shape looks like, and you can see right now it's being expanded. If you want, you can make the scaling factor negative, and that should contract the shape. So this is the first shape we created. And remember, This tool is not meant to be precise. It's meant to be approximate. And let's look at the second shape. What does that second shape look like? And here, this is what the second shape looks like. You can see the shape looks a little extreme, and that's because of the scaling factor. I think if we make this a true scale, that'll look a little better. Or maybe let's go back to model scale, maybe change the scaling factor a little. Right, so here I've modified the scaling factor so it looks a little better, but that's okay. Let's go ahead and move on to the third shape. That would be a shape here. And then the fourth shape. Let's look at that. So remember, the first few rows, the last M rows correspond to the 4 shapes that were created in the web app. Now, the first N rows of this data correspond to the 4 design cycles during the optimization. So 1, 2, 3, and 4. If you click on this first row and click apply, let's go back here and maybe switch this to true scale. This is going to give you the actual shape change after design cycle 1. And this, if you select the second row and click apply, this is the shape change after design cycle 2, 3, and 4. And let's rotate this a little. And let's look at what the shape looks like for this part of the model. Right. So this is what the final shape looks like after the optimization. And you might be asking, okay, how do I animate this? Select all 4 rows here, mark the checkbox for animate, and click apply. Now, you could do a few things here. You can pause it. You can manually go through the shapes. Or you can specify more frames, if you will. So if you go to the far right-hand side, type in maybe 40 frames and click apply. And this is going to create a smoother animation of the shape change. So let's go ahead and let this go to 40 frames. If you want to, you can slow down the animation or speed it up. It's really up to you. Here, I'll go ahead and speed it up a little. And this is what the shape looks like. Here, one comment to make. In a moment, I'm going to show you that this element here was the element with the high stress value. You can see what the optimizer has decided to do. To make sure that the stress is low for this element, it's actually decided to smooth out, for the most part, that corner. And it's when you smooth out that corner that you're able to minimize the mass while at the same time making sure the stress is within the upper bound of 40, I believe. Now, the same can be said for this other region where we change the shape. So let's go ahead and look at this. So here we were able to actually contract these 2 shapes to minimize the mass in this region while making sure the stress is within our specified bound. Now, what is there left to do? We need to make sure that the stress value is under the upper bound of 40. So how do we do that? So in the F06 file, there is a section called, or it may actually not be available in here. Actually, it is. After each design cycle, you get this big section that summarizes the results of the design cycle. You get this table called design constraints on responses. And then you get a column either called value, input, or output value. These are normalized constraint values. These are unitless. You would get a normalized constraint value for the lower and the upper bound for each stress value. In this other section, responses in design model, you get another table, stress responses for subcase 1, 4, 5, 6, 7, 8, so on and so on. Here, these values are values that are actually in units of pascals or PSI. These are real world units, if you will. So here, let's look at this a little bit. For element 355, I get a stress value of about 39.75. And the same is true for these other elements. Now, I believe component 13 is going to be the center of the element. Let me go ahead and confirm that in my notes. Okay, things are looking good here. So after looking at my notes, yes, component 13 is the von Mises stress at the center of the hexahedral element. So now, what you need to do is combine these two tables together. You can do this manually, or you can do this with the web app. So let's go back here and open a different tool called the Responses web app. And let's upload that F06 file. So this has combined those two sections, the unitless constraints and the real world constraints. And let's click on this button, maximum constraint for each design cycle. Each design, or rather, out of all the constraints, one constraint is selected as the most severe or violated constraint. That normalized constraint is what's plotted here in the max normalized constraint plot. So negative 0.07, negative 0.029, and so on and so on. After you click this blue button, you'll see that these values in this column correspond to the values in this plot. So now, since I now know the normalized constraint values for each design cycle, what are the corresponding von Mises stress values? For the initial design, I get a max stress of about 36.8. For the final design, I get a max stress of about 39.98. Click on this blue icon to show more information. Here, I'm told which elements are the elements that are producing this high stress. So let's go ahead and go back to these results and click on fringe. And now, this is where we have to do some manipulation. Here, the next few rows, I believe it's 24 rows, correspond to the 12 statics load cases. And now, why do we have 24 load cases when we originally had 12? Half of these load cases are for the initial design, whereas the other 12 are for the final design. The final design load cases are marked with this suffix D4 for design cycle 4. So here, if we wanted to, maybe what we can do here, just to save some time, let me look at the F06 file actually. And here at the final analysis, let's just pick one of these values to confirm. And it seems that element 356 for subcase 4 is the element producing the highest stress. So subcase 4, let's go ahead and hunt that subcase down. So this is subcase 1, 2, 3, and 4. And we're looking at the final design, so we'll select D4. Let's go ahead and look at this. And maybe we want to turn off averaging, so let's go ahead and turn that off. Let's look here. Maybe we want to look at the center. Perfect. So here we see that for the final design, for subcase 4, the max von Mises stress at the center of the element happens at element 356, which corresponds to what we have here, this row. 356, component 13, which is the center of the element. Now you might be asking, why is it 39.98 here, but it's 40 in Natran? rounding. That's why. Now you can repeat the process for another element. Maybe if we look at subcase 5. Let's look at subcase 5. So let's go back here and select subcase 5. And here we get a value of about 33.9 at a different element. But we were looking only at a few elements here in this region. Oh, too many elements. So I'll say this. We didn't constrain all the elements. There were only a few elements that we constrained. So let's look at that right now. So this is going to be element 355. Let me see if I can find that element actually. I want to find element 355, 353. Let me change the color. Oh, here it is. Click apply. Good. So we're getting values of about 25. Right. So here you can see we're getting values of about 25 and 26. And this is what we get back in Natran, 25 and 26. So there you have it. That was a very quick shape optimization for a more complex component that you might find in a real world scenario. Let me end it off with a few final remarks. So number one, if you want to learn more, I recommend that you refer to the appendix in the workshop. And I recommend that you refer to the introductory shape optimization workshop of the cantilever beam. The appendix also has a lot more information about shape optimization. So I recommend that you also look at this exercise. And one last thing, as always, if you have any questions or comments, if you want to apply these concepts to your own structure or mechanical system, if you want access to the Sol 200 web app, you're more than welcome to contact me at this email address. With that, I'll stop here and thank you so much for watching.